if we have specific glycans on our biopharmaceuticals that are not found in humans, the whole biopharmaceutical can become even toxic for humans.
Hey, smart scientists. Welcome to another episode on the Smart Biotech Scientist podcast. How can we tune the quality, the stability, the safety of biologics? Well, one way is by changing the glycosylation. And I'm having a conversation today with Thomas Rexer, who is the CTO of eversyn, a spin-off company of the Max Planck Institute in Magdeburg, Germany. And we are talking about in vitro glycosylation and how you could use that to tune the quality of your molecules and how we can make that affordable. So stay tuned for an exciting conversation. Welcome to the Smart Biotech Scientist podcast. I'm your host, David Brohlman. Let's smarten up biotech. Welcome, Thomas. It's great to have you on the show today.
Hi, David. It's my pleasure to be here.
Thomas, share something that most people don't know about you.
I think what most people don't know about me is that I play football. So I play football here for a local club. Now, because of age, I don't play, I think, regular for the normal team anymore. I usually play for the older guys, I would say. But every now and then I do appear for my team at the normal level. And yes, I think that's what most people don't know about me. It's really my second passion after biotechnology. And yeah, I hope I can continue to play and enjoy football.
Yeah, that's fantastic. And let's talk about your first passion, biotech. So how did you get started in biotech and how did you get to the place where you are at today?
I got started in biotech when I was a bachelor student. So my interests were always the natural sciences and also specifically biology. But then I started to study process engineering and did a bachelor thesis in the biotech field. But to be honest, at that time, I didn't enjoy my supervisor very much. She was very tough. And then I gave up biotechnology for some time, but the interest didn't die completely. So then later, when I had my PhD, I came to the Max Planck Institute in Magdeburg and joined here the bioprocess engineering department. And this was more about modeling biosystems, but then very fast, I also went into the experimental section again. Ever since then, actually, I've been back to the biotechnology field and have been enjoying it very much, to be honest.
Wow, that's exciting. And now today you're CTO of eversyn. What is the mission that drives you today as a CTO in a startup company?
Even so, I really enjoy the academic field. I never really had the plan to stay my whole career just in academia. And from when I started here, we always had the idea to commercialize the technology we are building. And it really took some time to really mature the technology. But then on the other hand, you also want to have the right team in place because obviously in biotech, it's very hard to start a business by yourself. And then when I felt the team is there, the team is mature, the technology is mature, then we really started our efforts to commercialize and spin out the technology. And this is where we stand right now. We are on the verge of leaving the institute and really starting the business. And it's been really exciting. And I'm looking forward for the next month to come.
Yeah, that's definitely exciting. And we're going to touch upon it in the second part of our interview, where we're going to look at the pros and cons of being an entrepreneur and the challenges and what is exciting about it. But before we do that, let's talk about science. Can you provide our listeners just a brief overview of what you're doing? So you are working in glycoengineering. And what is glycoengineering and what is the significance of glycoengineering?
That's a very good question. So if we look at the best-selling drugs nowadays, most of them are actually biopharmaceuticals. In fact, they are glycoproteins. And what does glycoprotein mean? Glycoprotein means you have the amino acid backbone, and conjugated to this backbone are sugar residues. And these sugar residues, they are called glycans. And over the last decades, we have learned that these glycans, they fulfill different function. And depending on the function, you can improve your biopharmaceutical. And I think in the biopharmaceutical industry nowadays, there is a trend to really harvest tailoring these glycans and improve the properties of the biopharmaceutical.
Now, I can't hide my passion for glycoengineering and glycosylation in general because I did my PhD on glycoengineering. So I'm really excited to have a conversation with you on that, Thomas. But for those who are listening and are not so familiar with glycosylation, can you explain why it's important to change the glycans to tune them, and how can you use that to enhance the properties of therapeutics proteins?
Yes, there are actually multiple ways how you can enhance the protein. So we know, for example, that if you leave out a specific sugar residue, you can improve something called ADCC, which will increase the efficiency of your antibody. And then by extending the glycan in a certain way, you can also improve blood circulation. So the biopharmaceutical stays longer in your blood. And of course, then this would mean that you can use lower doses. Another aspect which we learned, I think, in the last decades is that if we have specific glycans on our biopharmaceuticals that are not found in humans, the whole biopharmaceutical can become even toxic for humans. So this was also a very important lesson to be learned. Actually, there are multiple ways how you can improve the properties of biopharmaceuticals through glycoengineering.
Now, there are different ways to engineer your glycans there. You can work on the cell line. You can work, what I did in my PhD, on the media components, on the environment you're cultivating the cells in. And you are choosing a different way to do glycoengineering. So can you just give us a quick overview of how you are engineering the glycans?
Yes. So what we develop is a technology called in vitro glycoengineering. And this method is completely independent of the upstream processing. This is one big advantage, right? Because you can design your upstream processing in the way that you think is best. And in vitro glycoengineering, basically what happens is that you use recombinant enzymes and also substrates called activated sugars. And then as part of the downstream processing, you apply these two things to tailor the glycosylation in whatever way you want to tailor it. And why it hasn't been applied yet, I think one reason is that the activated sugars are extremely expensive, not available in large amounts typically, but also you need to have efficient enzymes that you can also produce efficiently. Yes, you mentioned it also. You're also very passionate about glycosylation and glycoengineering, and you did your PhD in, I think, media optimization. And actually, this is something I would really like to ask you also. What do you think are the advantages and disadvantages of the media optimization and the cell line engineering? Be very excited, I think, also for your audience to learn your aspect on that, since you've been working with this many, many years.
Absolutely. Well, what I like with media optimization, it's definitely the big advantage is that it's relatively simple. Once you find a media component or supplement that influences the metabolism of a cell, you can relatively easily fine-tune glycans. I think that's the beauty of this aspect. The drawback, obviously, is you can only adjust the glycans so much within the cell's capabilities. So somewhere you will reach a limit and you cannot go beyond because the cell doesn't have or capacity to change the metabolism. But definitely the advantage is the simplicity and it's relatively quick. Whereas if you want to change the cell line, obviously to engineer the cell line, you have pretty much any possibility, but we all know that this is no easy undertaking. So that's definitely the advantage. You mentioned, Thomas, the high cost currently in vitro glycoengineering. What other challenges do we currently face in glycoengineering?
There's maybe one thing following on what you said, what I would also like to ask you, and you talked about the advantages and disadvantages, but how scalable are these things like cell line engineering and cell culture, media optimization? I understand you worked in your PhD. This was probably tech scale, but what can you say about scaling into production? Can you apply this in larger setting or?
Yeah, that's the beauty of the media optimization. It's very easily scalable. And I was very fortunate during my PhD because we identified several compounds that worked and we very quickly implemented them in the development workflow. And whenever there was a promising result, they tried it at larger scale. And yes, it's easily scalable because you understand the process. And whether you do it at a very small scale or larger scale doesn't affect the biology, because what you need to keep in mind when you do media optimization, it's the environment the cell sees. And this environment, whether it's in a 3.5 liter bioreactor or in a 15,000 liter, it doesn't change. If you do the scale up right, obviously. But more on that on other episode on the scale up. But if you do it right, it's very easily scalable.
Okay. I think one point that you mentioned is very interesting, and you said you can use this technology to tailor this glycosylation within the range of what the cell is capable of doing. And I think this is also where in vitro glycoengineering comes in, because this is something that is completely independent of what the cell can do, what cell you are using, how you design your upstream process. In vitro glycoengineering is really independent of that and can produce your biopharmaceutical, and then you can, as a second step, as part of the downstream processing or as a separate step, you can tailor the glycosylation. And I think one advantage is also, we know that sometimes when you do the upstream processing, you end up with batch-to-batch variation, and this is completely eliminated by in vitro glycoengineering. And also typically the yields that you gain, the yields that you produce are also in a very high range. So if you target a specific glycan that you want to produce, you can typically produce it with 95%, for a yield of 90 to 95%. And I think another aspect that I would like to mention is also that I understand that from media optimization, you can produce specific glycans, but with the in vitro glycoengineering, you are completely flexible. You can basically produce any glycan that you want. And I think this is really also a significant advantage of the approach. Yes.
So what I'm hearing is that with in vitro glycoengineering, you can cover pretty much the entire range, let's say from 0 to 100% of a specific glycan. And you have also the possibility to do this in a very targeted way.
Exactly. Yes.
Yeah, and that's where I see definitely, obviously, I'm excited about in vitro glycoengineering as well. I think the combination of, let's say, media optimization and in vitro glycoengineering, with that, you can pretty much do anything. But more on the cost side later, I think this is probably still the biggest, if I understand correctly, Thomas, this is the biggest hurdle we have right now with in vitro glycoengineering, right?
Yes, I would say this is one of the biggest hurdle. You need the activated sugars, you need the glycosyltransferases, and what we have developed here is really a technology where we can produce the activated sugars at a tiny fraction of the costs that are currently there. And I mean, when I talk about costs, you need to imagine that these activated sugars at the moment are more expensive per mass than gold, right? This really tells you how expensive they are. And I think if you access to these activated sugars in large amount and also cheap enough, the in vitro glycoengineering technology will become very interesting. But also other ways of producing glycans, for example, as part of other drugs or other vaccines, I think this will become really interesting. And we believe there will be an application for this, an application that will improve the quality and the safety of biopharmaceuticals. And yeah, it's very exciting to be part of this, to be honest.
So what needs to happen, Thomas, to drive down these costs significantly so we can use it, let's say, in a large-scale facility?
Yes, so what we have developed is a multi-step biocatalysis process. And what does this mean? So we designed novel pathways, novel in vitro pathways, using recombinant enzymes produced in E. coli that can convert very cheap starting substrates to the activated sugars. And this really took us some time because the design of the pathway, you can do this, but then you need to test whether it functions. And what takes a very long time is actually the optimization of the pathway to really get good yields, good final titers. Yes, and this is where we stand at the moment. And we think the technology is ready to be applied and produce activated sugars, but also to produce glycan.
That's great. I'm very curious about how your biocatalysis works. But before we do that, I have another question just about the glycoengineering, Thomas. Can you share a specific example of a successful glycoengineering strategy? Because for those who are not so familiar, I think it would be interesting to see what you can do by applying these amazing tools for in vitro glycoengineering.
Absolutely, yes. So in 2013, 2012, we saw the approval of the first glycoengineered monoclonal antibodies. So one was Gazyva, developed by Glycard, was approved in 2013 for the use against leukemia. And this monoclonal antibody was glycoengineered in a way that two enzymes were overexpressed, two enzymes of the glycosylation pathway. And this inhibited the attachment of fucose to the glycan structure of the monoclonal antibody. And in Japan, exactly the same happened, but in another way. So in Kyowa Biotechnologies, they developed monoclonal antibody named Botelingo, and they also avoided this fucosylation, but not by overexpressing the enzymes, but by knocking out fucosyltransferases, which is the enzyme in the glycosylation pathway that attaches this fucose. And these two antibodies, they were the first one to be approved. And as far as I know, they are still on the market. Since that, we have seen that 4 more glycoengineered antibodies enter the market, and I think there's certainly a trend to glycoengineer antibodies.
Hey, smart scientists, this is it for today. I hope you've gotten as much value out of our conversation with Thomas Rexer as I have. Thomas Rexer is the CTO of Eversyn, a spin-off company of the Max Planck Institute in Magdeburg, Germany. And in the second part, we are going to continue our discussion on glycoengineering, and then he's going to tell us why he has become now a CTO of a startup company and what are the challenges and why you should too try this exciting journey as an entrepreneur. So see you in part 2. All right, smart scientists. That's all for today on the Smart Biotech Scientist podcast. Thank you for tuning in and joining us on your journey to bioprocess mastery. For additional bioprocessing tips, visit us at smartbiotechscientist.com. Stay tuned for more inspiring biotech insights in our next episode. Until then, let's continue to smarten up biotech.